Yo, this is second session of 27th February 2025. I'm going to start homomorphisms of vector bundles. So, how do we define this? So, let v let v be a vector bundle over M, and phi prime be a vector bundle over vector bundle v prime over n. V2 vector bundles. Homomorphism F. Okay, math. I'm still getting used to the snippets of math actually. A homomorphism F tilde from V to V prime is a smooth map such that there exists f m to n for which the following diagram commutes. The following diagram commutes. Cool. What is a diagram? I'll of course just pause this and attach the diagram and come back quick. Alright, I did transfer the image from my notes. So fig, it will be h, and then the images vv homo.jpg, yeah, around vector bundle homomorphism. Fig, I don't know, vbh. Okay, cool. So we define the vector bundle homomorphism as this smooth map between these two total spaces such that there exists a map between the base spaces such that through the projection maps this following diagram commutes. And by following diagram commutes, by commuting in this case we mean that is the fibers from M are mapped to fibers in are mapped to fibers in N, fibers of N. So what we mean is f tilde of v underscore x by v underscore x, we mean the fibers at x and M is the fibers are in the fibers at N, fibers at f of x in N. Yep, that's what we mean. And there is a fiber to fiber linear map also at each point, and clearly f v underscore x to v prime underscore f of x is a linear map. It's a fiber to fiber linear map. Is a fiber to fiber linear map. Yep. We can similarly define an isomorphism, which I've already indicated in the last recording, that well, we'll just begin another definition. Let pi v to m and pi prime v prime to m be two vector bundles over m. An isomorphism tilde f from m v to v prime is a diffeomorphism. It's a diffeomorphism, not just a smooth map, it's a diffeomorphism such that the following diagram commutes. So diffeomorphism, then the meaning of commutes is more stronger here, and we'll be back with a quick image. Yep, I'm back. The image is loaded. So the following diagram commutes. Which diagram we specifically mean is VB iso.jpg vector bundle isomorphism VBI. So yep, there you go. So that is f tilde of Vx is precisely V prime underscore x. And of course, similarly, and the fiber to fiber diffeomorphism is actually a linear isomorphism, and del f to v underscore x to v prime underscore x Okay, I'm really getting bad at typing here. Oh shit. Really getting bad at typing here. Is a linear, is a fiber to fiber linear isomorphism. Yep, there it is. Okay, there it is. Since it's a linear isomorphism, f tilde vx to vx, it's the matrix is actually invertible, and locally I think it follows that f tilde is a diffeomorphism. Yeah. So let's see some examples. So first example is simple smooth map from, it's a smooth map from between two manifolds, smooth manifolds, smooth map, then define the smooth map. We define a smooth map between tangent bundles of these two manifolds, right? Star from Tm to Tn such that f well, I'm really getting bad at this typing thing. Why? Yeah, because everything is all oh yeah, never mind. P comma v maps to f of p, first coordinate, sure, and then push forward at p of the vector v, tangent vector v. Right, so this defines the tangent bundle homomorphism apparently. So it's good to draw the projection maps from Tm and Tn to the m and n and see that f star is smooth, and then there is a map f between m to n, which is there is already, and the fibers are mapped into the fiber from m to into n, right? And then we need to also show that the fiber f star maps the fibers linearly. Yeah, f star is a linear map indeed, because it just takes tangent vectors from other tangent vectors, and we've seen that already. It's derivation. It's basically it's differential. Sorry, differential at each point. Yeah. So time for another image. I'll make it quick. So we are live again. I have added the image. So let's just run this now. The first example is this. With the homomorphism, it's clear from the picture. Which, oh my god, tm homo.jpg tangent bundle homomorphism dbh dmh. Okay, cool. Right, so from the image it is clear that the fibers are indeed mapped into the fibers of n, right, precisely, because the tangent vector, we want to put it into the tangent vector of n, and the differential exactly does that job. So that is a nice one. We need to show and f star is linear map. Define f star is a linear map because it's a differential. F star is a linear map. Because f star p is linear for each point between m. and then we need to show f star is smooth. So here's the thing, f star is smooth. We need to go down to the charts level and see that these are indeed smooth. So what we'll see is basically that since f is smooth, it is something like phi o f, phi inverse. It just follows from the fact that f is smooth, and yeah, f is smooth, and also there's a Jacobian factor. I mean, let's see, right? So it'll look familiar, right? Let u comma phi be a chart of m, and v comma psi be a chart of n, such that f of u is in v. Okay. Further, we have let u comma phi be a chart of dm, basically phi tilde maps du precisely to phi of u times rm, right? Further, and dv comma psi tilde be a chart of dn, so tilde psi maps from dv to psi of v times rn. Now there is a map from tu to tv through f star, and then to show phi star is smooth, we basically need to consider following intermanifold transition function, if you wish to put it that way. So start search tilde phi inverse of x comma c. X comma c is in phi of u cross rm is equals to psi circ f circ phi inverse of x comma yeah, it's so thing is, when you go to Rn from tu to Rm locally, tu to phi of u cross Rm locally, you are essentially taking the coefficients of the tangent vector on Rm, right? And then you are okay. So yeah, and then you'll also consider the same thing for TV, coefficients in Rn. Now, how these two are related, how these two coefficients are related, we can actually derive that, similar to one we derived while doing the tangent bundles. in two different charts. So yeah, it's good to recall. It's good to recall that. Let's just go back. Two tangent bundles. So yeah, here there's linear coordinates related by change of coordinates to the Jacobian matrix. Yeah. Yep, precisely. Yeah, I mean, the details are there, and all those go through them. Okay, where am I? Okay. Wait, what? I think what we can do is chart of the n. Then star is precisely, yep, this is the Jacobian psi surd f surd phi inverse x times c. Yep. I just use one left and there is, oh, I see. Whew. This is indeed smooth. Yeah. I think it's good to also go back and make sure you understand these things. Yeah. Changing. Okay, once you do that, you apply it on some point. Yeah, exactly. Mm-hmm. You apply precisely on the functions like kth coordinate phi of p. Also be determines. Why side? Uh-huh. Yeah, just need to. Yeah, then there will be a phi. Exactly. F. Yeah. Since okay, I see. I see. Makes sense. That makes sense. So this is smooth and so F star is smooth and is a vector bundle. Homomorphism between Tm and Tn. Cool. Something interesting consequence is if f is an embedding, then so is f star. In the above example, if f is an embedding, then f so is f star. Okay, this work this out in the notes. So you locally see what as f star star. Then you will realize that the determinant f star star is precisely given by the determinant of, since f is an embedding, f star is injection. So the derivative of f star star is so the derivative of it is actually depending on the injection of f star. So since f star is injection, f star star is also an injection apparently for all points, and the homomorphism needs to be worked out a bit actually. So for now I will not go into the details of this. Also the next one, in fact, I'll work this out from tomorrow more substantially. If M is a subset in N is a regular submanifold, then Tm, a subset of N, is also a regular submanifold. Okay. More importantly, I mean, but in particular, U phi is an adapted chart of M, then Tu comma is an adapted chart of Tn. This is something to be checked, okay, and I'm interested to do it, so do it. The fourth example in this series is okay, this is a special case of these things actually, special case of the above two results, that f or more importantly that the tangent bundle is a regular submanifold of T of another space if N is a regular submanifold of another space. These need to be sort of sat down and checked properly with a good headspace. I mean, yeah, it's hard to do it when you're lost in all these calculations, right? So anyway, here TRN is isomorphic to diffeomorphic to Rn plus N. So yeah, I mean, with P comma Ci PD PDV partial Xi vert P maps to P comma 1 from dot C underscore N is an isomorphism of vector bundles over vector bundles over Rn. See, so if M is a regular submanifold, then Tm is a regular submanifold, because TRN is isomorphic to Rn cross Rn as vector bundle. In fact, it is diffeomorphic as manifolds. But yeah. Next example on this part of this is Sn is a regular submanifold of Rn plus 1 plus 1. Yeah. This one with such that it's a regular submanifold. So Sn is a regular submanifold of Rn, so Ts2 is a R6. Okay, so I don't appreciate this enough, I think, I'm not sure. Then Tsn equals to comma v and norm of 1. Let's just quickly norm symbol in LaTeX. Yeah, how to write this? Norm of x? Is that a thing? Yeah, I mean, so it makes sense. Norm of, oh, no idea that works. I think just typing norm will suffice. Norm of 1 x equals 1 comma x comma v equals 0, right? With the tangent bundle over Sn is this, right? Something wrong? Yep, it is something wrong. And what the hell is this undefined control sequence? I don't understand what's the undefined here. Oh, I see. Okay, so I need to go and what? Use use package bracket. I don't know. Cool. Works. So well, I mean this is, I don't know why I'm doing this, but these are just as examples of other, right? as examples of the above example. Showcases of this. Okay. I mean, if n equals to 2, ts2 equals to set of x comma v in r3 times r3 mid square plus x2 square plus x3 square equals to 1 comma v v dot x equals to 0. That is plus v underscore 2 x underscore 2 plus v 3 x underscore 3. I'm not able to give you comments here, but yeah, for the good part, we have sections on the vector bundles. So definition, let pi v to m be a smooth vector bundle. I think that's about 9 sections. There are many kind of sections. L1, L2, measurable, etc. So we will not deal with those things. But yeah, we'll define what are smooth sections next, but for our purposes this is the definition we want to work with. If pi v to m is a smooth vector bundle, a section S m to v is a map such that pi circ S is equals to id m. So basically, you take a point in M, map it to one of the points in its fiber. Cool. That is, S of x is in the fiber at x. Okay. Quick image again. Back with figure. What the fuck? this, and what is sec.jpg, sections of a section of a vector bundle, sec. Cool. So that's our image, and we say that S is a smooth section if S is a smooth map. Simple. Let's of course get to the examples. So the first example is on the trivial vector bundle. If V is equals to M plus Rk is a trivial vector bundle over M, which can be projected to M. I hope this is right. Yep. Then a smooth section S from M to M cross Rk is basically S of x equals to, first thing is x, and then f of x, because it should map to some Rn, right? Rk. So where f m to Rk is a smooth map. So that pi of s of x is x.
Yep, I mean it does satisfy, right? Just projection. Yeah, I mean just numbering anyways.
So S on a trivial vector bundle is determined entirely by F. There is another example. Pi from any vector bundle is a vector bundle, and is 0 of Vx. So in each fiber map, you define the section to map from a point on M to the vector bundle, to the total space, via z of x is equal to 0 of the vector space of the vector space. I think it's better if I just write it as 0. the vector space is actually a smooth map. It's a smooth section. It's a smooth section. So how do you show the smoothness of the section? Smooth section. Okay. Smooth section because section. Let u comma phi be a chart of M such that trivialization h pi inverse of u, okay, that's that it is a local trivialization. Okay, so we consider a chart on V on M such that we have a local trivialization on V. Okay. Local trivialization, then what you need to show is Z is smooth. To show Z is smooth, we consider the following compositions actually: U over set or U mapping from via Z to pi inverse of U. Pi inverse of U. Pi inverse of U is subset of V. Pi inverse is locally trivial. Via H. So h of z of x is equals to x comma 0. What are we missing here? Yeah, 0, okay. Since H is a diffeomorphism, it precisely goes to 0 of it, and basically H of Z is clearly, since H circ Z U to U cross RK is smooth, Z is also smooth. Because H inverse is smooth, and then we can just put back. Okay, fair enough. Yeah, what we need to show is basically z smooth. So you pi inverse u is locally trivial, go to u plus rk, can go further down phi of u times rk. That is not necessary in fact. Can go, and then u can go to phi of u. So yeah, x to x comma 0. Further down it's again phi of x to phi of x comma 0, which is smooth, so z is smooth. Simple. Okay, that finishes week 6 lecture 1. We'll go for local sections from next recording. So okay, yeah, we'll go to local section in next recording. Let's take a break.